Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll start our topic of determinants and see how the new structure determinants helps us in simplifying solutions of problems we've already seen, such as how to solve a system of n equations containing n unknowns. So determinants are a subset of matrices. That means not every matrix has a corresponding determinants, but some do. As a matter of fact, only square matrices. So every square matrix has a determinant corresponding to it. Now, the biggest difference between a matrix and a determinant is that a determinant has a specific value. There is no such thing as value of a matrix. If I give you a matrix 1, 3, 2, 5, you can't ask me what is the value of this matrix. There is no such thing as a value. It is a matrix which is a collection of 4 numbers, 2 in the first row, 2 in the second row, 2 in the first column, 2 in the second column. But there is no single number that specifies its value. However, corresponding to this square matrix, there will be a determinant. And the determinant is simply written just like the matrix, except instead of square brackets, we just have 2 bars around it. So if this is the matrix, this is the corresponding determinant. And I'll show you how to calculate the value of determinant in a second, but before that I'd like to talk about the unconventional definition we had for matrix multiplication. When you add 2 matrices, you add corresponding entries. When you multiply a matrix by a number, you multiply each entry by that number. But when you multiply 2 matrices, you cannot just multiply corresponding entries. It's actually a little bit more complicated than that. Now, why is it a little bit more complicated? Because that is the definition which helps us to simplify a lot of mathematical problems, such as when you say alpha is a transformation on beta and gamma is a transformation on alpha, then it is a product of 2 transformations on beta, which transformations can be represented as a product of matrices of individual transformations. Similarly, the value of a determinant has a somewhat complicated formula. It is not a very simple value. Now, why don't we define it to be some simple value? Why do we define it to be a complicated formula? Again, the answer is the same, because that complicated formula enables us to simplify calculations. If I just said that the value of the determinant, say, is the sum of the 4 numbers, then that's very good, but then that wouldn't be very useful to us, and somebody along the way would create another mathematical construct which would have a complicated formula and which would help us in simplifying problems, and that is the thing which you would be studying, as opposed to what I call a determinant, in which you added the 4 numbers. So the value of a determinant is somewhat complicated in terms of the formula, but that complication exists only because once we deal with that complication, a lot of other formulas and solutions become very easy. So the value of a determinant is different for different orders. What is the order of a determinant? It is the number of rows or columns. Now, why did I say rows or columns? Because, like I said, a determinant is only valid for a square matrix, and a square matrix has the same number of rows and columns. So if we have a, let's say, 5 cross 5 matrix, let's say 1, 2, 3, 4, 5, 2, 3, 4, 5, and there would be entries here as well. If we had a 5 cross 5 matrix, that would give rise to a 5 cross 5 determinant, or a determinant of order 5. It would have the same structure 1, 2, 3, 4, 5, 2, 3, 4, 5, and there would be entries here as well. So the order of the determinant is the number of rows and columns. Now the value of a determinant is quite straightforward for a 2 cross 2 determinant. Actually, there is such thing as a 1 cross 1 determinant, but it would just be a simple number. If you have a matrix which has just 1 row and 1 column which has a value 2, it would have a corresponding determinant, and that determinant would have the value 2, right? So we'll just keep increasing orders. For a first order determinant, the value of the determinant is simply the value of the entry, because there is only one entry. Now let's look at 2 cross 2 determinants. So if we have, let's say, a matrix A, B, C, D, then the corresponding determinant would be A, B, C, D, and the value of this determinant is given by AD minus BC. So the way to remember it is the downward arrow comes first. So AD and then BC. You always cross multiply like this. A into D and B into C. And since the downward arrow comes first, it's A into D minus B into C. So this is the value of this determinant, a 2 cross 2 determinant or a determinant of order 2. Now what about a 3 cross 3 determinant? So let's say the determinant is A, B, C, D, E, F, G, H, I. Now this is a 3 cross 3 determinant or a determinant of order 3. And to get the value of this determinant, we use a method which is often called expansion by rows and columns, rows or columns. So we can take any row or any column and we can expand it about that row or column. So generally we just take the first row. So if we expand it about the first row, we'll take these 3 entries and we'll expand the determinant about these 3 entries. So first we'll take A. Now A will be multiplied by the determinant of E, F, H, I. So what we've done is, I'll put this all into a rigorous formula in a few moments. Right now we just need to know how that formula comes about. And again, this definition is quite complicated. Initially you might think, what's the point of this complicated definition? But as we'll see in the next video, among other places, that this actually makes calculations very easier. Remember how we talked in a previous video about some matrices which have an inverse, and we said we will be able to calculate that inverse after we've done determinants? Well, that's because this complicated definition enables us to calculate the inverse very easily, among other things. So A times the determinant of EFHI. Now what that means is, if you're expanding it about this row, then you take these 3 entries. The moment you take the first entry, you multiply it by the determinant you get by eliminating this row and this column. So if you're expanding it about this row, then initially you'll take A. Now A will be multiplied by the determinant or the value of the determinant that is obtained by eliminating the row and column in which A exists. So if it's a 3 cross 3 determinant, you take out A, you take out that row and that column, it's a 2 cross 2 determinant. Similarly, you'll have B, and B will be multiplied by the determinant you get after you remove the row and column to which B belong. So for A, you removed this row and this column. So what you were left with, EFHI. For B, you removed the first row and the second column. So what you will be left is DFGI. And then you take C, and then you take the determinant which will be left by removing the row and column to which C belong. That means removing the first row and the third column. So what you will be left with is DEGH. And then you don't actually add them up. There's one more little bit of trickery. Here there is a minus sign. So it's plus, minus, plus. And the rule for determinants generally is, it goes like plus, minus, plus, minus, plus, minus, plus, minus, plus. And we'll extend it to higher order determinants in a moment. But this is the way you do it. If you were expanding it about the first row, then you take the first entry, multiply by the remaining determinant. You take the second entry, multiply by the remaining determinant. Take the third entry, multiply by the remaining determinant, and then you have this formula. So it will be plus here, minus here, plus here. So the determinant of a 3 cross 3 matrix, the value of the determinant of a 3 cross 3 matrix, we get that in terms of the values of 2 cross 2 matrices, 2 cross 2 matrices or 2 cross 2 determinants. Right. Now, what if we wanted to expand it about, let's say, the second column? Well, that's easy. It's minus plus minus. We'll take care of that later. But first, we are expanding it about the second column. Right. I'll just write the determinant here again for the sake of clarity. So again, we'll take the first entry, that is B, multiplied by the determinant you get by removing this row in this column. That is DFGI. You take the second one, that is E, because now we are expanding it about this column instead of the first row. Multiplied by the determinant you get by removing this row and this column. So it would be ACGI. And then you'll take the third one, that is H. And then you have the determinant you get by removing this row and this column. That would be ACDF. And you follow these signs, that is minus plus minus, so minus plus minus. Now these two things you can try for any random determinant will end up giving you the same value, which it has to, because that's what we call the value of the determinant. You could expand it about the third row, about the third column, or any other line, right? So a good way to remember this plus minus plus is that every row, every entry has the power minus 1 to the power j plus k, where j and k is the row and column. So first row, first column, 1 plus 1, 2, minus 1 to the power 2 is 1, so it's a plus. First row, second column, minus. Second row, first column, minus. So if you're talking about the entry in the jth row and the kth column, it has a sign in front of it given by minus 1 to the power j plus k. Right. We've covered a lot in the last few minutes, so I'd like to repeat it once. A single order determinant has the value A. I told you that for a second order determinant, the value is AD minus BC. But now you can see that in terms of the formula as well. The signs for it will be plus, minus, minus, plus. You can expand it about any row, any column. Let's say we do it about the first row. Then A times the determinant you get by removing this row and this column, that will be D. And then you have B times the determinant you get by removing the first row and the second column, so only C will be left. And of course the first row has the plus, the second row has the minus. So every nth order determinant will have a value that is given in terms of a number of n minus 1 order determinants, and you get that by n minus 2 order determinants, and so on. So for the first one the value is A, second one using that formula we get AD minus BC, third one. Now I'll just try to use numbers now to make it a little bit more clearer. 1, 3, 7, 2, minus 4, 6, 3, 9, 2. Its value we need to find. Now one thing I need you to be careful about, we keep doing this minus this, AD minus BC. And when you're doing that and there's a minus sign in front of an entry, there is a high probability of somebody making an error of a minus sign. So when you're doing these problems, make sure you're a little bit extra careful about that. So now we'll just expand it about what? Let's expand it about the third column. Okay, so first of all the signs for it will be plus minus plus, minus plus minus, plus minus plus, given by minus 1 to the power j plus k. So this is the first row and third column, so 1 plus 3 is 4, minus 1 to the power 4 is 1. So we're expanding it about this column. So first we'll take 7, we'll take a determinant with that. We'll take 6, we'll take a determinant with that. And we'll take 2 and we'll take a determinant with that. And this will have a plus sign, this will have a plus sign, this will have a minus sign. So this term minus this term plus this term. Now what are the determinants? For 7, we just remove this row and this column, we get 2 minus 4, 3, 9. For 6, we remove this row and this column, we get 1, 3, 3, 9. And for 2, we remove this row and this column, so we get 1, 3, 2, minus 1. By the way, when you get, let's say when you take 6 and you remove this row and this column and you get this determinant 1, 3, 3, 9, the matrix 1, 3, 3, 9 is called the submatrix of the bigger matrix and the determinant is called the subdeterminant. So if you were to ask me what is the submatrix of 3, that means you just remove this row and this column, whatever is left is the submatrix. So you get 2, 6, 3, 2. Now you can try it about any other row and column and you should end up getting the same value. right? Now let's try to make it a little bit more formal and try to put it in terms of formulas. So before that, I'd like to define a few quantities. The first term is the minor. Now we saw what order was. Order is defined for a determinant. If a determinant has 7 rows and 7 columns, then it is a determinant of order 7. Right. Now minor doesn't exist for a determinant, it exists for each entry. So if the entry is Ajk, then the minor is often written as Mjk. And the minor is nothing but the subdeterminant of Ajk. So the minor is the determinant we get after removing the jth row and the kth column. So if you have a matrix X, Y, Z, let's take 4 entries: W, U, V, P, Q, R, S, T, A, B, C, D, E. Then what would be the minor of, let's say, V? V is the entry in the second row and second column, right? So it would be basically M22, and that would be a determinant we get after removing this row and this column. So if we want the minor of this entry, remember, order is defined for a matrix, a minor is defined for each entry. These are all entries. This is A11, A12, A13, A21, A22, and stuff like that. So if we want the minor of the second row and second column, we just remove this column and we just remove this row. And what is left? X, Z, W, R, S, A, B, D, E. Right. So minor is defined for each entry, and it is the determinant we get after removing the jth row and the kth column, or the row and column to which that entry belongs. E would have its own minor. E would be M44, and it would simply be, you remove this and this, and these 9 entries would correspond to the minor of E, or of the 4th entry, or the entry at the 4th row and 4th column, or A44. So every entry has a corresponding minor. Then you have something called the cofactor of Ajk. That is, it is also determined for each entry. You have a cofactor for each entry, just like you have a minor for each entry. And a cofactor is simple enough. It is written as Cjk, and it is simply minus 1 to the power j plus k mjk. So now you see we're getting closer to the actual formula. Mjk is the subdeterminant or the minor of jk. You multiply it by minus 1 to the power j plus k, which gives you sign, and this is the cofactor. And in terms of cofactors, the determinant is given as summation of j is equal to 1 to n, where n is the order of the determinant, Ajk Cjk. Where k could have any value. K could be 1 or 2, n, but k has a single value, right? So Ajk Cjk, which basically means A1k C1k plus A2k C2k plus dot 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 dot. Right. Now A1k, let's say you're talking about 1. Let's say you're taking k is equal to 1. Then this would be A11 C11, A21 C21, and stuff like this. A31 C31, third row and first column. So if k is equal to 1, this corresponds to an expansion about the first column. If k is equal to 4, this corresponds to an expansion about the fourth column. So this is a standard formula for expansion about columns, but we also have a standard formula for expansion about rows. And that is given as summation k is equal to 1 to n Ajk Cjk. where j can be any value 1, 2, up to n. So if j is 1, then this corresponds to A11 C11 plus A12 C12 plus A13 C13, first row, third column. So if j is 1, this is an expansion about the first row. If j is 7, this is an expansion about the 7th row. So after defining these structures, you see that the formula is quite simple enough, though still we see that the formula is dependent on the minors. That is, a 5 cross 5 matrix will have a formula in which you will have terms which are 4 cross 4 matrices. To get each of those matrices, you will have 3 cross 3 matrices. To get each of those matrices, you will have values of 2 cross 2 matrices. Right. So this is an expansion about columns, this is an expansion about rows, and this is the general formula for calculating the value of a determinant. I'd like to again remind you, why are we using this complicated formula? Because this makes a lot of calculations very easy, as we'll see in the next video. Right. So now let's move on to some properties of determinants. And by the way, I'm not going to prove the fact that you can expand about any row and any column and the value would be the same. That involves a little bit complicated mathematics which is not in your course. But I suggest you try it for 1 or 2 determinants to expand it about multiple rows and columns and see for yourself that the value indeed is the same. The first is a 0 row or column. I'm just going to write r/c for row/columns because we'll use it again and again. A 0 row or column means that the value is 0. How do we know that? Let's say we have a 7 cross 7 matrix with the 4th column consisting only of zeros. Everything else has a non-zero value, but the 4th column has zeros. Then what do? You expand it about the 4th column and you'll have 0 multiplied by something, 0 multiplied by something, and you can see that the value will come out to be 0. We've already told you, then you can expand about any row or any column and the answer will be the same. So why not expand it about this column, which will give the value 0. So if any row or any column has a value 0, that means every entry in a particular row or a particular column has a value 0, then the determinant has a value 0. The second is identical or even proportional rows or columns means the value is 0. It's easy to see that for a 2 cross 2 matrix, if you have A, B, let's say, 2 identical rows, then the value will be AB minus AB, which will be 0. So it's easily proven for a 2 cross 2 matrix. What about for a 3 cross 3 matrix? So let's say you have A, B, C, D, E, F, D, E, F. Well, if the second and the third row are the same, then you can expand it about the first row. And every time you take the minor of an entry, you are going to get a subdeterminant with identical rows. So its value will be 0. That means A times this minor, B times a minor, C times a minor. All the minors will have a value 0. And then you can extrapolate to 4 cross 4 or higher matrices as well. If you have a 4 cross 4 matrix, you'll expand it in terms of 3 cross 3 matrices. And if a 4 cross 4 matrix has identical rows or columns, then at least one expansion about a non-identical row or column will have 3 cross 3 matrices which will also have identical rows or columns, and hence their value will be 0. Now the same goes for proportional rows or columns. So if instead of D, E, F you have 2D, 2E and 2F, that still means the same thing, because you could take a 2 common outside and then you could have D, E, F. Because if you're expanding it about this row, let's say, then you'll have 2D multiplied by something, 2E multiplied by something, 2F multiplied by something, in which you can take 2 common outside and you'll again have D times something, E times something, F times something. Right, so this is true for proportional rows and columns as well. The next property is that multiplication of a row, actually we used this in the previous proof, of a row or column by a constant means the value is multiplied by that constant. So let's say you have 6A, 6A, 6B, 6C, D, E, F, G, H, I. Now it is in a single row. If you have this in a single row, then the value of this determinant is equal to 6 times the value of the determinant A, B, C, D, E, F, G, H, I. Right, because this value will be 6A multiplied by something, 6B multiplied by something, 6C multiplied by something if you're expanding it about the first row, and then you can take 6 outside. So multiplication of a row or column by a constant implies the value is multiplied by that constant. Now remember, this has a very interesting correlation or a corollary, which is that the determinant of CA, where A is a matrix, right, C is a number, is not equal to C times the determinant of A, it is equal to C to the power n times the determinant of A. Because if you take a matrix A, B, C, D, E, F, G, H, I and you multiply it by, let's say, 6, then the value will not be 6A, 6B, 6C and D, E, F, G, H, I. All of these will have a 6 multiplied by them. Right? So if you multiply a single row or a single column by a constant, the value is multiplied by that constant. But if you multiply every entry by that constant, then this will be the determinant's value will be 6 to the power 3 times the original value, because you will get 6 out 3 times. Right. So determinant of C times A is not C times determinant of A, it is C to the power n times determinant of A, where n is the order of the determinant or of a matrix. Another property, transposition. By the way, whatever we define for square matrices goes on for determinants as well. You can have symmetric determinants or skew symmetric determinants and so on. So transposition of a matrix or determinant, generally it's used for matrix, means that the value is unchanged. So let's say you have A, B, C, D, E, F, G, H, I, and you have the transpose of this matrix A, B, C, D, E, F, G, H, I. If you don't remember what transposition is, we've done it in a previous video. So what you do is you expand this by the rows. So A times E, F, H, I determinant, B times D, F, G, I, and C times D, E, G, H. Right, so you get a particular relation. Now you expand this by this column and you'll see you get the exact same relation. A times E, H, F, I, B times D, G, F, C, which has a minus, and C times D, G, E, H, C times D, G, E, H. Right, so you see that you will get the exact same relation, and so you can see that the transposition of a matrix means that the value of the determinant is unchanged. Right. The next rule, the interchange of two rows or of two columns means that the value is multiplied by minus 1. Right. Now how do you see that? Let's say you have A, B, C, D, E, F, G, H, I. And the second one, let's say you interchange the first two rows. So D, E, F, A, B, C, G, H, I. Now here you expand about the first row, here you expand about the second row. So A times E, F, H, I. Here also you'll have A times E, F, H, I. Right, so all the three terms will be the same, except that the signs will be different, because the signs are plus, minus, plus, minus, plus, minus, plus, minus, plus. So in the first case you're expanding out the first row, and here you're expanding out the second row, which have opposite signs. So the value of the determinant will be multiplied by minus 1. Right, and the final property, addition of a multiple of one row or column to another row or column means that the value is unchanged. This is sort of like adding a multiple of one equation to another equation when you solve linear equations. So let's say you have A, B, C, D, E, F, G, H, I. This was the original matrix. Now what you do is you add, let's say, 4 times the third row to the first row. So you get A plus 4G, B plus 4H, C plus 4I. Now you can actually separate this into 2 matrices, 2 determinants, because every time you'll have A plus 4G times something, B plus 4H times something, C plus 4I times something. So you can actually write this as A, B, C, D, E, F, G, H, I plus another matrix 4G, 4H, 4I, D, E, F, G, H, I. Right, because A times E, F, G, H, E, F, H, I, 4G times E, F, H, I will be A plus 4G times E, F, H, I. So you can work this out on your own. You can see that this result indeed does hold. And we know that if you have 2 proportional rows or proportional columns, the value is 0. So in this case, the value is unchanged. So we've seen a lot in this video about determinants, how we created a new structure after matrices and we defined its value in a complicated way. In the next video, which is titled Kramer's rule, we'll see the biggest use of determinants, which is in solving linear equations by Kramer's rule, and some other uses as well. For example, how to calculate the inverse of a matrix. Thank you.